We'll address Raghu's query and then we'll start the class. So star OK equal to 10 is fine. OK equal to ampersand of 10 should give error, syntax error. 10 equal to OK should give syntax error. Plus plus OK plus plus, I don't know. OK plus plus minus minus, I think that is not valid. And the same thing should be true for plus plus OK plus plus. So all the other errors, star OK equal to 10 should not be a problem, right? Oh, I see. Star OK. Yeah, but this information will not be captured by the syntax. That we have to look at OK's type, and therefore star OK equal to 10 should not be given as syntax error in assignment 1. 10 equal to OK is an error. OK equal to ampersand of 10 is an error. Plus plus OK plus plus should be an error. OK plus plus minus minus should also be an error because it doesn't return L value. So therefore, it should not be. Ampersand OK equal to 10. I think that is not supported in C. It is, I mean, the reference variables are there in C++. So ampersand OK equal to 10 should also not be supported. In star star OK equal to ampersand of ampersand OK. No, I don't think this is correct. The ampersand of ampersand OK should also not be a valid syntax. I think you can take ampersand only once. Right, so except for star OK equal to 10, all of them should be errors. Whether all these errors are going to be captured by the test cases or not, I am not sure. But yeah, as far as what we expect from the syntax analyzer is that except for star OK equal to 10, all the things should be errors. Okay, so let's start the class. And feel free to use Moodle if you have further questions, not a problem. You can also ask in the class, but the TAs may not be there. So, all right. So we looked at top-down parsing. Within that, we looked at specifically LL1 parsing, and we constructed a nice predictive parsing table after creating the first and the follow sets. A very similar notion exists in the bottom-up parsing, but it's projected in a slightly different manner. The terms are going to be a little different, but conceptually it is very similar. There is definitely going to be something different because we are now going to go from bottom up, and what bottom up means is that you are going to have the string available with you, the string that you want to parse, that is the program, and from there you want to reach somehow the starting state. Right? So that will make sure that that particular string is derivable from that starting symbol. Alternatively, we can say that that string can be reduced to the starting symbol. So we construct the parse tree bottom up. It so happens that in practice you may not construct an explicit tree, but the reductions that you do that can be abstracted as a creation of a tree, and it's called as a reduction. So at each reduction step, a specific substring which might contain terminals and non-terminals which match the body of a production, which match the right hand side of the production, that gets replaced by the left hand side non-terminal. Right? So that is the head of the production. So that is what we want to do all the time. So for example, you start from the string id into id. This I would like to convert into, let's say, f into id. Right? So this is where I am now at the at the leaf of the tree. From here I am now going to construct an interior node f, which is going to derive the id, and that is how is the f into id I get. Once I have f into id, that I need to replace with t deriving f, so it becomes t into id. T into ID I need to convert into T into F by having that F derive the second ID. T star F becomes T, and then T is derived from E, and that is how we get the original the syntax tree corresponding to ID star ID. So there is a reduction happening. Each string containing terminals and non-terminals is going to get replaced by the left-hand side of the production loop, right? Because we have T deriving F, and therefore F gets replaced by T and so on. Again, the question arises that which production to use, and in general you might require backtracking. However, it so happens that for special classes and most of the constructs in programming languages can be nicely captured without backtracking by having a single look ahead. Right? That is what will also be true in the case of bottom-up parsing. So a reduction is the reverse of a derivation, top-down versus bottom-up, and therefore the goal of bottom-up parsing is to construct the derivation in the reverse order. Right? So we are going from left to right. We should be able to derive this left to right sequence from right to left, right? So we have ID into ID that gets converted into F into ID and T into ID and so on. This was our reduction sequence, right? If I reverse the arrows, what we get is the E deriving T, T deriving T star F deriving T into ID, right? So what I am doing is that when I have T star F, I am actually if I look at it in the reverse order, T star F is getting converted into T into ID. That means that F, which is the rightmost non-terminal, is getting replaced or getting derived from rather than T. So this seems to be the rightmost derivation. Is this clear? So even again T star D, well, T star D in that I should have replaced. Yeah, so that is correct. So the ID is already there, and therefore from T there is the only one non-terminal, therefore it becomes F into ID and so on. So as you can see in ID1 into ID2, ID1 is going to get replaced later. ID2 is going to get derived first when you follow this right to left order, and therefore this is the rightmost derivation. So the goal and this rightmost derivation we are going to do in the opposite order. Right to left is top down, left to right is the bottom up, and therefore the goal of bottom up parsing is to scan the input from left to right. You are still reading the input as ID into ID and so on, and you are going to E all the way. So that construction of this tree is happening in the rightmost derivation, but that happens in reverse. Any questions so far? We have quite a few people today. 38 seems to be a good number. And why is that? Again, some test or something? Okay, anyway. All right. So, a few nomenclatures in this. So handle is essentially the right hand side substring which you want to replace by the left hand side non-terminal. So handle is a substring that matches the body of the production, right? And reduction of a handle represents one step in the reverse of the rightmost derivation, right? So each of these is a handle. So I'll just show you how this people might have forgotten about class at 8. Okay, all right, no problem. So starting from ID into ID, although we are going all the way to E, how that stepwise happens, that I am going to show now. Right? So the just for the sake of exposition, I am going to number these as ID1 and ID2 so that we are able to distinguish. So the handler here is going to be ID1 because that is the one that is going to get replaced by the F as the non-terminal. So F deriving ID is the production. Right hand side of this production is ID, and this ID1 is going to get replaced by F, and therefore it becomes F. Okay, let me just yeah, so that becomes F. So therefore the string now becomes F into ID2. In that the handle is F again. How is it? I mean, assume that there is some oracle right now which tells us that only F should be replaced and not F into ID2 and so on. So considering that that is somewhere we have those magical powers, so F becomes the handle, and that T deriving F is the production. So now that F turns into T, right? So that is similar to what is happening here. Within T into ID2, ID2 now becomes the handle, and therefore F deriving ID gets kicked in, and therefore now this becomes T star F. From T star F, T star F itself is the handle, right? Neither T, I mean T could have been a handle for E deriving T, but that is not going to happen because of our look ahead. So T star F is going to be the handle completely. That is going to get replaced by T, and therefore T now becomes the handle, which is getting replaced by E, which is the starting symbol. So this is how the pruning of the handle. That means that you have this right hand side, and that is going to get replaced by a smaller non-terminal, possibly smaller non-terminal. So therefore this is called as handle pruning. Okay. So the goal of bottom-up parsing is going to follow this order, and how to get exactly the correct handle, that magical power we are going to get with our look ahead. Okay, and we also say a handle. For example, where I have mentioned reduction of a handle, we have mentioned a handle rather than the handle. The handle is going to be the case in case of our whatever grammars we are going to look at, whatever is derivable with single look at, but otherwise we will have to say a handle, because the grammar could be ambiguous for that particular K value. So we are going to talk about the bottom-up parsing, LR parsing with K as the look ahead, like we had LL parsing. So therefore anything beyond that K look ahead is going to be not recognizable by that particular grammar. Therefore the grammar we can say is ambiguous for that LRK grammar. Okay. Okay, let's move ahead. By the way, I forgot that we should congratulate Anderson for 600 wickets. Okay, so let's come to this interesting part, which is again a type of parsing. This shift reduce parsing is an implementation. Right? So bottom-up parsing, like top-down parsing, one of the implementations was to do the implementation using left to right scanning and then having the leftmost derivation, etc. So shift reduce parsing is also another way of implementing these bottom-up, not another, a way of implementing the bottom-up parsing. What it does is that it has a stack which holds those grammar symbols, where we just saw the rightmost sentential forms. So all these sentential forms are going to get stored in this stack, and we expect, or the way it is designed, the handle always appears at the stack top, and that is a good thing, because then you are always going to be taking advantage of just having the stack top giving us the information, and therefore you should be able to see some connection with respect to the context free grammar, because we are essentially using a push down automaton. Okay, so these operations shift reduce, this shift means that you are going to push the next token to the stack. Where is the token coming from? That is coming from the lexical analyte. This token shift action means that it should be pushed on the top of the stack. Reduce means that I need to identify the handle on the top of the stack and replace it by the left hand side non-terminal, and again push that onto the stack. There is also one more action which is going to be there in the shift reduce parsing. What will that be? So in LL parsing, what was the special action that we had on the starting symbol and the last character in the input? Right. So it is going to be an accept thing apart from shift and reduce. Right? So when will you accept? Now that I have told you the procedure, that this is what we are going to do with the stack and the handles and so on, when will you say that a particular string, which is the input program, belongs to the language? So when will you go into the accept state with this machinery? Stack has S and only dollar is left. Stack is empty, empty stack acceptance. Okay, so PDA thoughts are coming into your minds. Okay, yeah. So acceptance not by empty stack, because we said that when we say T star F, that needs to be replaced by T. So that T needs to be pushed back onto the stack. So at the end, the way Raghu has mentioned, it will have the starting state and the input should be over. That input should be over is an important part, because otherwise you might have an expression like ID plus ID plus. So as soon as you have identified ID plus ID, oh, this seems to be the belonging to the language, and therefore, and the top of the stack, not only top of the stack, stack contains only S. But then the input string is not pointing to the end of the string, and therefore we have to be careful. So both these conditions are required, that the stack, not the stack top, the stack contains only the starting symbol and the input is over. At that time we will say that the string belongs to the language. Right, when we replace the handle and stack has S. Okay, so that input string is an important criteria. Okay, so let's try this shifting and reduce on the example that we have been seeing, and then we will come to the actual parsing table and so on. So let's look at it carefully, and this is what actually is going to happen. We have these two data structures, the stack and the input, and then there is some action which is going to be there, which is either going to be shift or reduce or accept. Initially, so I am going to mark both the bottom of the stack as well as the end of the input using dollar. So initially stack is empty, input contains ID1 into ID2 dollar. At this stage I am going to apply the shift. Again, how I am deciding whether it should be shift or reduce, that we are going to see a little later, but assuming that we have those oracle powers with us, I am going to do a shift. That shift is going to push that ID into the stack, so that becomes $ID1 at the top of the stack, and now the string contains $ID2. At this stage I am going to reduce, so therefore that becomes $F. So as soon as I reduced ID1 to F, I am going to pop ID1, replace it with the left hand side non-terminal and push the left hand side non-terminal into the stack. So that gets here, then I am going to apply T deriving F, so that becomes like this. Then I am going to again do a shift, that becomes T star, then T star F, and so on. So all of this is similar to what we have discussed. Finally you have T at the top of the stack and dollar, and here I can apply the production E deriving T. Therefore the stack now contains only E and the input is over, therefore you can accept the string, right? And you can try with different combination like we have done in case of the predictive parsing table, the top down parsing. You can try other strings which don't belong to the language, and you should see that either the stack will not be empty or the input will not be over, and therefore we will not be able to accept the string. Okay, let's move ahead. Yeah, so shift reduce parsing, I think we have mentioned that. So this is an important part. The handle appears at the stack top prior to pruning. So I'm going to just mention those steps here in the algorithmic form, pseudocode form. So initially the stack is empty. String W is on the input, which is $. During left to right input scan, important thing, it is still left to right scanning. Right? So in case of shift reduce parsing, and a special form of shift reduce parsing is LR parsing, where I am going to use again left to right scanning, but I am going to use the rightmost derivation in reverse order, and therefore that R appears compared to what we had in the LL parsing. So left to right input scanning is going to be there unless you are talking about Arabic languages. So parser shifts 0 or more input tokens on the stack, right? And then the parser might as well reduce a handle to the head of the production, and this cycle gets repeated until error or accept happens. All right. So this is what was our algorithm. I'm just putting it down for understanding. Okay. So let's come to this conflict. Some of you might have come across these conflicts while designing the YARC grammar. So there exist context-free grammars for which shift-reduced parsing cannot be used. So there is a limitation to shift-reduced parsing. Like LL parsing, you cannot, for example, do the if-else, the nested if-else construct using the LL parsing. In case of LR parsing, while you will be able to take care of that, you will face some other trouble with, for example, context-sensitive languages. Those you won't be able to parse using the context-free grammar. And we'll see a couple of such examples. So even if you have the complete knowledge of the stack, not only the stack top, but complete knowledge of the stack, that is, you are using it as an array, as a random access memory, and you have a very large K look ahead, the parser may not know whether to shift. Shift meaning I am going to delay the processing of the reduction. Reduction means that you are making progress. So I am going to delay, I am going to look at more and more input. Therefore, I am being lazy. Or I might be eager and I might just reduce the current contents on the stack to a non-terminal. So that if it is unable to figure out this, then we call that as a shift-reduce conflict. This we have also discussed in the context of if-else. So otherwise, there might be a possibility that two different productions might match the same handle, and in such cases there is a reduce conflict. Epsilon productions are that way very notorious to generate reduce conflicts, so you should be careful. So I'm just mentioning this here for the sake of completeness, but most of it we know all of this. So if expression then statement else, and the input contains else $, right? So in such cases, depending upon what the programmer intended, programmer meaning the programmer of the compiler, that is the compiler writer, that else whether it matches with the latest if or the earliest if. So it may be correct to reduce if expression then statement to statement, or it may be correct to shift the else part. So we can add more let's say constructs in the YARC parser to make sure that the precedence is given to one of them. So in general, we say that shift-reduce conflict is not a showstopper, because you can do away with it by providing these additional flexibilities like precedence, etc. But in general, it should be avoided because you can get into issues. It can generate an erroneous parser. And we have seen that ID plus ID into ID. If you have ID plus ID as the reduction, as the gets reduced, then you are going to get a wrong answer, unless you have used percent precedence. Right? And in case of reduce conflict, for example, not in C, but in case of languages such as I think Fortran, where the matrix operations are specified using parenthesized expressions. Right? So let's consider this where ARR of I comma j, right? That gets. So those of you who have done Fortran, is this the syntax for the array expressions ARR of I comma j? And can the functions be invoked as fun parenthesis a comma b? Can people confirm? Otherwise, we have to say that this is some fictitious language. Okay, thank you for confirming. Okay, so assume that this is the syntax where we have ARR of ij and fun of ab, and all of these are identifiers, and therefore it is not clear whether you should be reducing it as an array expression or as a function call. Right? So, so in general, just by looking at the syntax, it becomes difficult, and these are usually end cases. It's not that the compiler writers are unaware that such a problem occurs. They are aware, but they have to also have the syntax which is kind of programmer friendly. Right? So they might have decided to have such a syntax and take care of this in a special manner. So in this case, for example, that special manner means that you have to consult the symbol table, find out if ARR is an array or whether FUN is a function call, etc. Whether FUN is a function and so on. So depending upon the type information, then you will take a call that what particular reduction you should be using. However, this goes beyond the syntax. So your context-free grammar is unable to give you this distinction, and therefore you have to consult the type information. So it becomes beyond context-free. Right? It goes into the semantic analysis. Okay, so that's our shift reduce and reduce conflicts. Yeah, so another alternative is that instead of YARK consulting the symbol table, even the lexer can consult the symbol table and generate different tokens for array and function. But again, it goes back to having additional flexibility beyond regular expression and context-free grammar. Okay. Another example that we had seen some time back was ABCD into EFGH in the context of C, where it could either be a pointer declaration, a pointer definition, or it could be a multiplication expression. Right? So that also is a problem. And as I was mentioning that theoretically one might say that, oh, you should not have shift reduce conflicts, but in practice it is okay to have. I mean, maybe not for your assignments, but when you are designing a very complicated new language, it's okay to have it. As an extreme case, you might have a couple of reduce or even shift reduce conflicts. It's okay as long as it is helpful for the programmer. And then you have additional mechanism to take care of removing this ambiguity. Because finally, at the end of the day, it's for the humans, right? So your language should be reasonably easy to program. For that reason, you are introducing a new way of representing, let's say you are adding some sort of punctuation symbol there and so on. That seems a little problem for the programmer. Okay, so let's come to this. Who are these hero and heroine? Girinath, do you know that? Who are these hero and heroine? Raj Kapoor again. Nishit is hooked on to Raj Kapoor. Mumudki na dek Mumudki. Naman Rishi Kapoor. Oh man. Okay. Rishant, who is this? Who are these people? Rishika, who is this heroine? Okay, no problem. Okay, Deepesh is saying Devanand. Okay, that seems to be a correct answer. Aryanti is saying Oda Rahman. Good. Okay, so we have some people who know about at least some of these. Yeah, I should have probably taken hero heroine from maybe Telugu cinema. That would have probably fetched more answers. But anyway, I think many of you feel that everybody that whom I show is somewhere related to Sarthak, right? All of these Rishi Kapoor, Raj Kapoor, etc. Anyway, so why am I showing all of this? So this is some song from a movie, and the song goes like this. I'm going to not sing, but I'm just going to tell the lyrics here. Otherwise, even the small number of 43 students will also go away. Let's start singing. So the lyrics are अपनी तो हर आह एक तूफान है ऊपर वाला जानकर अनजान. Right? So the exact meaning is not very important, but that ऊपर वाला is something which is interesting. In Hindi or Urdu, that means the one above, right? And that gets usually it usually means that you are talking about the God. However, in this train journey, the statements are a little ambiguous, and it's not clear whether he is referring to the God who is above or whether he is referring to the passenger who is above. Right? And Veda Rahman's parents, I mean the heroine's parents, are also there in the same coach, and they are all the time wondering what is this song referring to. Right? So definitely what I am talking about is ambiguity, and our English language is ambiguous to a very good extent, not only Hindi but almost all the spoken languages. And this ambiguity sometimes creeps into the programming languages also, like we were talking about the reduce conflicts. Talking about punctuations and ambiguity, there is very interesting statement. I'll just type it on the chat box, or maybe I can say it. Panda eats, shoots, and leaves. Right? So, sorry, that is panda. Panda eats, shoots, and leaves. This can be interpreted in two ways. One is panda eats bamboo shoots and leaves of the tree. Other is the panda eats, shoots, and leaves. Right? So, where you put the punctuation, that changes the meaning of this sentence. In fact, there is a book on by this name, Eat, Shoots, and Leaves. What I'm trying to say is that there are ambiguous statements, and even in programming languages there are times, and we have to make sure that this ambiguity gets removed. By the end of the song, even the parents are aware that he is not talking about the passenger, but he is talking about the god. But anyway, that may not be the case depending upon what the director wants. Okay, so let's come to the specific implementation of this shift reduced parsing, which is called as LR parsing. So far, any questions? Not on the movie, but on the compiler part of it. Okay, so if there are no questions, let's talk about this LR parsing. So we said that we are going to scan the input from left to right, and we are going to use the rightmost derivation in the reverse order. Right? So you should definitely go back and look at that f into id, etc. Where f into id happens, where id into f happens or f into id happens, that is going to tell us whether it is rightmost derivation or leftmost derivation. Right? So there are different types of these bottom-up parsers. One is called simple LR. And that simple is usually a nomenclature. Like those of you who are probably aware that when you perform the tax declaration, the form, the very, very complicated form that you fill in, what is that form called? Your parents must be filling it up, but ITR, yeah, very good. I am happy to know about this. I don't know if because of internships whether you were forced to fill up ITR. But there is the form which you fill up. This ITR is income tax return, but the form that you fill up, it has a very interesting name, similar to what I have mentioned as the name of the LR parser. So it is called Sahas form. Sahas is simple, easy, and definitely it is not that. I mean, I don't know who came up with that name, but yeah. So we have this simple LR as one of the types. When we are going to look at the canonical LR, which is going to be a more powerful version of this. However, it is very complicated. It's very inefficient, and there is a possibility of improving the efficiency at the cost of some precision. When I am talking about precision, I am talking about adding possibility of ambiguity. Right? So that is the power of a parser. Right? So that's what I am calling as a precision. However, it turns out that you don't really require the precision of canonical LR. Even if you have some possibility of ambiguity, the possibility of occurring that is so low in practice that you can do away with it, and therefore that you get additional performance because of that. And that is called as a look-ahead or LLR parser. Look-ahead is going to be there even in others, but yeah, it is still called as LLR parser for traditional reasons. This LLR parser is what your YARC generates. So in general, like LLK parsers, top-down parsers, we have LRK parsers for the bottom-up case, and for almost all our practical purposes in not only, I mean, primarily programming, not only me, primarily programming, we require at max one look-ahead symbol, the way our constructs are designed. That doesn't mean that somebody cannot come up with a construct which requires maybe 5 look-ahead symbols and so on. You might have such a language, unlikely that it will become successful. And this LR grammars are the most prevalent grammars today. As I was mentioning, even YARN generates LLR parsers. Okay, so why LR? One specific interesting thing about the power of LR, it turns out that LR grammars, it's a strict superset of what LL grammars can recognize, right? That means that all the top-down parsers, if you put together for a particular K, right? If you can put together all the languages that get generated or recognized by these LL parsers, you will always be able to recognize those using LR parsers and more. So, and one example you definitely know about the if-else part. So, and in general, it recognizes all the programming language constructs. In fact, as I was mentioning, LL was not considered to be very practical until early 90s. But in some limited settings, when your programming language is not very complicated. For example, we are talking about general purpose languages, but there are special purpose languages like we discussed in the first class itself. That, for example, PostScript or something related to HTML or let's say even the strings that we give as commands on the Google search. All of these have a small embedded language, or let's say some other searching in colon unread in the Gmail box, etc. All of these are programming constructs. These are very simple. I can't write a for loop in the Gmail search. So when you have very limited such syntax, even regular expressions might be sufficient. And if there is slightly more complicated stuff, even LL parsing might be sufficient. So that is what I am saying, that for arbitrary programming languages you require something more than LL, but otherwise LL suffices. And another important point, which is very similar to LL parsing, is that it is non-backtracking. We don't want to backtrack. Backtracking is in general considered to be problematic, although in practice that is not always the case. But for example, in case of as soon as you have backtracking mechanism, let's say you are solving a maze, you suddenly get that exponential factor. Although it is constant to the power number of turns, but that exponentiation always creates a problem in computer science. It so happens that if you have the number of such turns finite, it might still be okay. Not finite, but maybe constant. It might still be reasonable in practice. Unfortunately, that is not going to be the case in programming languages, and therefore backtracking is not something which is going to be useful. We are going to have lots of different constructs, and therefore backtracking and going to another production is not considered to be an efficient solution, or not even practical solution. So we will have to have non-backtracking parsers. For that, we need to look ahead. Right? So that is where LR1, LRK grammars are going to come into picture. Right? So let's talk about simple LR. So simple LR that we have, definitely it's going to be based on the shift reduce parser. So you have the stack and the next input symbol to decide the action. But the issue comes in as that whether to shift or reduce, and that requires us some knowledge of the context where we are. Right? So where we are, I mean, it is context-free grammar definitely, so I should not be probably speaking about the context from that perspective, but you do require some information about how much you have passed, right? And that gives rise to, so in case of LL we had this parsing table which was giving us some sort of context where we are in the overall picture. Similarly, we want to create a parsing table, even in case of simple LR. So for example, if the stack contains $T, that is dollar is the bottom of the stack, T is at the top of the stack, and the next input symbol is star, should that be shifted for T star F, or should that be reduced anticipating E deriving T? Right? So this requires me, so if there is a table which says that if the stack top is T or the handle is T and I am talking about star as the next input symbol, then I should apply T star F. Right? If that is given to me, then my job is done. In fact, then such a parsing table will help me without backtracking to recognize a particular string. Right? So that is what we would like to build. That requires us to construct something called as items and item sets. Might be a little confusing initially, but once you get the hang of it, it will become clearer. It's a little tedious, but please hold on to that. But any questions so far? So this will require some concentration. Okay, so let's talk about these items and item set. So what we say is that the decisions for the shift reduce, whether to do a shifting or the reduce, that is done by maintaining some sort of a state. That state is similar to the state in the context, in the finite automaton, right? And that state tells you where we are in the parsing stage. That state is going to be a collection of items, and therefore we need to talk about items. So here that item set, a set of items, is what we are going to call as a state. So I'll define that. For example, if I have A deriving x, y, z, then I can talk about that I have seen none of the input. That is the first, that dot that I am showing, that means that I have not consumed any input. Or I might have seen the string corresponding to x or the substring corresponding to x. I am going to now look at y and z coming into picture, and I have not seen y and z, and that is shown using x dot yz, and similarly xy dot z or xyz dot, where I say that I have seen all of the input and that matches the complete handle, the complete right hand side body of this particular production. So this is getting into a little fine-grained details of where we are in the context. So far we didn't distinguish across these different states in which you can be. So these are different items that correspond to where I am in the parsing stage for this particular production. And depending upon where I am and the next input symbol, I am going to make some decisions. In fact, I am going to make some transitions in the automaton. So these are called as LR0 items. That means that 0, because I am not really going to look at the look ahead as of now. But this is where, just by giving the grammar, just by giving the input grammar, I am able to find out, just put dot at different places, and I am going to get this set of items. Together, this set of items or item sets we call as a state. And this state is going to be represented as a part of a state transition diagram. Right? So that's what we are going to see now. So special case of A deriving epsilon, it doesn't generate dot epsilon and epsilon dot, it just generates that epsilon is essentially empty string, so it just generates A deriving dot as an LR0 item. If there are any questions on this, please ask. Okay, so this part, once we have identified that this is what we are going to do, let's try it on a particular example. Right? So the overall, our goal is going to be that we are going to create this automaton, this finite automaton, which is called as LR0 automaton, just by looking at the grammar. So we find these sets of LR0 items from the starting symbol, and this starting symbol, for the reason that we need to have that end of the input, will augment. The first part we will do is to augment the grammar. So if you have S as the starting symbol, I am going to have S prime deriving S as the one more production, so that S prime becomes the starting symbol rather than S. That is just a simple addition. Then the closure is going to tell us, it is very similar to epsilon closure, where I am going to, if I am at a particular non-terminal, then where all I can go based on the position of that dot in my item set, that is going to give a closure. I am going to show an example that will become clearer. And then the third part is the transition. Right? So first part is I am going to augment the grammar. That means I am just going to add a start symbol, a different start symbol. I am going to have a closure by using these dots. Right? And then I am going to have transitions based on different symbols from one state, one item set to another. Once I have built this automaton, I am going to make use of this automaton to build the parsing table. Right? So let's come to that part. So if my grammar is like this, our expression grammar is like this, I am going to add this E prime deriving E as the augmented starting symbol. So E prime becomes my starting symbol now, right? This is just to have uniformity in case there are non-standard ways of representing start symbol, because start symbol might appear at other places also, right? Whereas that new start symbol will never appear elsewhere. So that will help us in the accept state. Okay, so let's move on, and we are now going to draw a big picture, right? So in the next 5 minutes, but let's see. I'll repeat that in the next one. So the first state that I'm going to mention is that I'm going to have E prime deriving E as the first item, LR0 item in this state. That means that I'm going to take the first, that is the new starting symbol, and I have not consumed anything, that is dot. Right? Now I'm going to, so this is the primary production in this state. Right? Since I have this primary production and that dot is preceding a non-terminal, that means that this state will also represent anything that is derivable from this non-terminal without consuming anything. That means that if dot E appears, whatever is generatable from E, whatever is generatable, whatever are the productions that have E on the left hand side, those also are possibly part of this particular item set. So what this means is that E deriving E plus T and E deriving T, both of these are also the productions which are possible, because I am representing E, I am at a place where I have not consumed anything, but E is possibly going to be the one that is going to get recognized. Right? And if E can get recognized, that means E plus T can also get recognized, and therefore T can also get recognized. Right? So that is what are these two derived items from these original item in this items. And this needs to be repeated. We come to a closure. As soon as we say that this now dot appears before this body of the production, E deriving E plus T, then that means that I need to now see E again, but that is going to give again the same two items, and we are talking about a set. Therefore, we don't need to add anything with respect to E now. However, the third item now has dot T. Therefore, whatever is derivable from T, that also can appear on top of the stack. Right? And therefore, that adds two productions corresponding to T here, T star F, and whatever I have seen, that dot appears just before it. Now that dot T does not add anything more, but dot F adds all of these, both of these into this particular item set, and since that dot precedes opening parenthesis, which is a terminal, similarly dot precedes ID, which is also a terminal, therefore it does not generate any new items in this item set. Therefore this has stabilized, this particular state or this particular item set has stabilized, and we get this closure which represents the complete state where you can be when you have not consumed any input symbol. Right? Is this state clear? Any questions on this one? Okay. So now with respect to LL parsing, when we said that we can do transitions based on plus and star and dollar, etc. Similarly here, you can do transitions based on different strings. Right? Those different strings are not going to be only tokens, but those different strings could also be non-terminal. So when I have consumed capital E by being in this I0 state, so that I0 is initial state, these are these fundamental items, or the main item which is not derivable from anything else is called as a kernel item, and the other ones are called as non-kernel or derived items. And this total kernel items and non-kernel items becomes the closure. So once I have, okay, fine. Okay, let's do this before we construct the final automaton in the next class. So find the closure set for T deriving T star F. What this means is that you are given this kernel item T deriving T star dot F, and now what are the other non-kernel items that you need to add? Anyone? Okay, so maybe something is unclear. Maybe you guys are f deriving dot e. Okay, since we have dot preceding f, therefore I can also be at a place where I have not seen anything which is derived from f, and therefore f deriving dot parenthesis e closing parenthesis is also going to be in the item set. Similarly, f deriving dot id is also going to be in the item set. Right? Okay, good. So that becomes the closure, and it does not add anything more. Therefore, these three, t deriving t star dot f and the two that Prashant has written, these three together will form one particular state. Right? And what to do with that? Well, essentially we are going to have transitions based on this. Okay, one more example. What is the closure set for this one? So what are the non-kernel items that you are going to add? Okay. Yeah, so we should not be adding any new extra items because we are going to, we have seen all of this. So at this stage we can make a decision whether we want to apply this rule or not. I mean, whether to apply this production or not, whether we can reduce it or not. Right? So that is what will be the decision that we will make at this stage. Okay, so we have done the augmentation of the grammar and we have talked about the closure. We'll study about the goto in the next class. If there are any questions, we can take those up now. Alright, if there are no questions, then we'll stop here. See you.